Hello everyone, this is Sudhanshu Sarkar, Assistant Professor, Department of Electrical Engineering, Narula Institute of Technology. Today I am going to talk on a topic of electrical circuit and network. This is very important for electrical engineering students because with the help of these electrical circuit and networks, that means the networks theorem, they will be able to solve different types of real life problem, and its application is very important for solving the real life real life difficulties like in transmission line, distribution line, for motor generators. So this concept is will be useful in every place of engineering. So for this subject the lesson plan is here, and here 3 units I will cover. So first unit in 2.3, unit 2, 2.3, there is parallel AC circuit, RLRC and RLC circuit. So today my topic of discussion is parallel RC circuit. So I'm going to talk about the different part of this parallel RC circuit, different properties of parallel RC circuit. So its impedance is admittance calculation, susceptance calculation. So it's about the parallel RC circuit. Now let me talk about that. What is this parallel RC circuit? So let me explain that first. In a parallel RC circuit, we already complete the series RLC circuit. So it is parallel RLC circuit is the exact opposite of the series circuit. Fine. So here in this circuit we have a voltage source, AC voltage source. Now with the voltage source there are three elements. One is the resistor, second is the inductor, and third one is the capacitor. RLC is connected and all are connected parallelly. And the current, the total current of the circuit is IS. So here Vs is actually representing the source voltage. It's a sinusoidal, that means the AC voltage. So from here the current is also generating, the current is IS, the total current IS is also given. Now in this point the current which is flowing through the resistor, that is IR, representing with IR. The current which is flowing through the inductor, that is representing with IL, and the current which is flowing through the capacitor, that is representing with IC. These are the three elements RLC, three current IR, IL, IC respectively, and the source current or the total current of the circuit is IS. The voltage source is Vs. So here that is the circuit. Now the circuit is again given in this here. So phasor diagram, we are going to draw the phasor diagram of series parallel RLC circuit. Look, we know that for series RL circuit, we already know that how to draw the phasor diagram, and for parallel RLC circuit, we are going to draw the phasor diagram. Now, for resistor, the voltage and current lie in the same phase. Look here, the IR and V both are in the same phase. So no problem with this part. Here the IC, we know that the capacitive current always lead at an angle 90 degree. So it is actually leading at an angle 90 degree. IC, capacitive current, is leading from the supply voltage at an angle 90 degree. That is the property of the capacitor. So no problem with this. And we know that the inductive currents always lag behind the voltage 90 degree. So it is also lagging 90 degree from the voltage V. So here in this point, if we redraw the circuit again, then we'll find the second diagram of the phasor diagram. So in the second diagram, it is written that IL minus IC. That means the circuit is a inductive circuit. For that reason, it is IL minus IC. So if it is a capacitive circuit, the value should be IC minus IL. So here, this phasor along negative y-axis is representing IL minus IC. As it is a inductive circuit, so we write here IL minus IC because the value of this IL is greater than IC. So this part will be IL minus IC along negative x-axis, and we know that along x-axis this is IR. So how can we draw the resultant current? We can draw it with the help of this IS phasor. So it is a vector sum of the IL minus IC and IR. So from the phasor diagram, we can easily understand that the value of IS, that is the supply current, that is equals to IS is actually the summation of IL minus IC plus IR. So that is our IS supply current. So in this way, with the help of phasor diagram, we can find the supply voltage. Now, the current triangle for the parallel RLC circuit. So using the formula of Pythagoras, we can say that IS square equals to from this part of the circuit, if we apply Pythagoras, then what will happen? IS is the resultant current, that is equals to IR square plus IL minus IC whole square. Okay, so now here from here we can easily write IS will be equals to root over IR square plus IL minus IC whole square. So in this way we can find the value of the resultant current or the total current of the circuit with the phasor diagram. Now we all know that using Ohm's law we can find that the current flowing through the resistor is IR. If it is IR, then this should be as per the Ohm's law V by R. The current flowing through the inductor in the circuit, if the current flowing through the inductor is IL, then this should be V by XL, supply voltage divided by inductive reactance. XL is the inductive reactance. Now for IC, this is V divided by capacitive reactance, that is XC, because the voltage across all the element is same V, because all are connected parallelly. Now simply put the value IR, IL and IC here, and after calculating we'll find that IS will be equals to V divided by Z. Okay, so in this way we can find the total current of a circuit, and the equation of the current is V divided by Z. So Z is actually the impedance of the circuit. Now it is very important, and this calculation, this equation will help us to solve the problem. So please remember all this for solving the complex circuit. Now here, since the voltage across the circuit is common to all three elements, the current through each branch can be found using Kirchhoff's current law. Using KCL, we can find because the voltage is same. Remember that Kirchhoff's current law or junction law states that the total current entering a junction or node is exactly equal to the current leaving that node. You all know from the KCL, it's the basic fundamental formula of electrical engineering. Thus, the current entering and leaving a node A are as above or given as. So what is actually KCL? Suppose we have a node. I might consider that we have 5. This is a node. You all know that what is node. The point is A. What is, suppose this is I1, this is I2. Now this is I3, this is I4, and it is I5. So how many incoming and outgoing current is there in this node A? Look, 2 incoming current, that is I1 and I2, and I3, I4, I5 is the outgoing current. So what is actually Kirchhoff's current law means? Kirchhoff's current law means that the incoming current, the summation of incoming current and the outgoing current are equal. That means we can easily write as per the KCL that I2 plus I1 incoming, both are incoming to node A, that should be equals to the current I3 plus I4 plus I5. So this is the formula of Kirchhoff's current law. Or in the other word, you can say the summation of incoming and outgoing current is equals to 0. How is it possible? So this is very easy because we have to rewrite the equation in some other slightly different form. What is that? If we consider that incoming current is positive, then I1 plus I2 will be positive. And as per the theorem that summation of all the incoming outgoing current equals to 0. If incoming is positive, then outgoing will be negative. But actually it is summation. So outgoing we consider, for the direction it is minus I3 plus minus I4 plus minus I5, that should be equals to 0. So that is Kirchhoff's current law. Now here we are going to apply this Kirchhoff's current law. So how can we implement this Kirchhoff's current law in the circuit? Now so we consider here a node A. So the incoming current at node A is Is, and the outgoing current is IR, IL, and IC. So we can consider all the starting this A as a common node because all the three connected parallelly. So we can consider A as a common node. So only one incoming current is here. Only this Is is coming, but this one, this one, this one, all the three is the outgoing current. So we can easily say that Is equals to IR plus IL plus IC. So that is the fundamental. So how they write here it is representing. Look, Is. So Is equals to, I write IR plus IL plus IC. So we write here in some different form, that is Is minus IR minus IL minus IC equals to 0. And we know now we have to put the equation of IR, IL, and IC. So what is IR as per Ohm's law? IR, we know that IR equals to V by R, V divided by R as per Ohm's law. So if there is a inductor in a circuit, the inductive current is IL, and what is the equation of IL? It is 1 by L integration V dt. That is the current, amount of current for the inductor. What is IC? IC is C dV dt. So just put the value for IR, this one, for IL 1 by L integration V dt, for IC C dV dt. So simply put all the values, and then we can find this equation. We can generate this equation, that is IS equals IS minus V by R minus 1 by L integration V dt minus C dV dt equals to 0. Now taking the derivative, okay, so what we have to take, taking the derivative, dividing through the above equation by the last page, the last line equation by C. Fine. So dividing the equation by C and then rearranging gives us the following second order equation for the circuit current. Okay, it becomes a second order. Yes, it is a second order equation if we differentiate it again. So equation becomes second order equation because there are two reactive elements in the circuit, the inductor and the capacitor. So what are the two reactive elements in the circuit? One is the inductor and one is the capacitor. So after differentiating, we get the equation Is minus d2 b dt2 dv minus dv by rc dt minus v by lc equals to 0. And then finally we'll get I of st, that will be equals to dv2 dt2 plus dv dt into 1 by rc, just rearranging, and 1 by lc into v. So we'll get this equation after derivative. Okay, so now impedance of parallel RLC circuit. So how to find, how to calculate, how can we calculate the impedance of parallel circuit? So we already calculate the impedance of parallel circuit. So for parallel circuit, the impedance is we know that the V R equals to V by IR. XL, the inductive reactance equals to V by IL. For resistance R equals to V by IR, inductive reactance V by IL, and XC, capacitive reactance V by IC. So Z is will be equals to 1 by R whole square plus, so it's a inductive circuit, so here this will be 1 by XL minus 1 by XC whole square. So the value 1 by Z will be equals to root over 1 by R whole square plus 1 by XL minus 1 by XC whole square. So in this way we can find the impedance of a parallel RLC circuit. Now the question is, how can we find the admittance of a parallel RC circuit? So first you have to understand that what is the relation between the admittance and the impedance. We know that the relation between the admittance and impedance is Z equals to 1 by Y. This Y is called the admittance, line admittance. So what will be Y? Y will be 1 by Z. So here, if you follow, you can find that 1 by ZT, that will be equals to YT, the total admittance. The total admittance is nothing but summation of all the admittance, Y1 plus Y2 plus Y3 plus Y4, etc. So here Y1 equals to, if Y equals to 1 by Z, then Y1 equals to 1 by Z1, Y2 will be equals to 1 by Z2, Y3 will be equals to 1 by Z3, and Y4 will be equals to 1 by Z4. So in this way we can Easily find the admittance of the circuit for a RLC parallel RLC circuit. Now here we are going to find the conductance, admittance and susceptance of a parallel RLC circuit. So what is the process to finding this? Let's talk about that. Conductance, admittance and susceptance. The units used for conductance, admittance and susceptance are all the same, namely Siemens. So the unit of all these three terms is Siemens, which can also be thought of as the reciprocal of ohms or ohm to the power minus 1. But the symbol used for each element is different, and in a pure component this is given as for admittance. We know that admittance is represented with Y. So admittance is the reciprocal of impedance. We already talk on this topic. That means reciprocal means Y equals to 1 by Z. Admittance, that means the admittance is the reciprocal of impedance. So Z is given by the symbol of Y. So Y will be equals to 1 by Z. So Y is equals to 1 by Z. The unit is Siemens. So in this way we can express Y. Now the second one is the conductance. Conductance represented with G. Conductance is the reciprocal of the resistance. So what is this reciprocal? We know that this is R. Reciprocal means 1 by G. Conduct. So we can write G is the reciprocal of resistance. So G should be equals to 1 by R. So that is written here. G equals to 1 by R. Now the third component is the susceptance. So what is susceptance? Susceptance is represented with B. Okay, so susceptance is the reciprocal of a pure reactance X. So susceptance has the relation with X, reciprocal of X. That means for inductive circuit, so susceptance is represented by B. So it is inductive susceptance means BL. So this will be equals to 1 by XL. And if it is a capacitive susceptance, so BC, that will be equals to 1 by XC, because susceptance is the reciprocal of reactance X. So if it is a inductive, then XL. If it is a capacitive, then XC. In this way, we can represent the three component: admittance, conductance, and the susceptance for parallel RLC circuit. Now, we can therefore define inductive and capacitive susceptance as follows. Our system is a AC system, so complex value will be there in this system. So BL will be equals to B angle minus 90 degree, because for inductive circuit we know that current lags behind voltage at an angle 90 degrees. So for that reason BL equals to B angle minus 90 degree. B angle minus 90 degrees equals to 0 minus JB. So I already talked on this topic several times, that how to convert R theta, means the rectangular to polar and polar to rectangular. So it is in R theta form. So you all know that X equals to R cos theta and Y equals to R sin theta. So using this basic formula, we can easily find that BL equals to B angle minus 90 degree, that is equals to 0 minus JB. And BC, for BC we know that current lead 90 degree from the voltage. So that's why the value of BC is equals to B angle plus 90 degree. Look very carefully. BC is B angle plus 90 degree. That means 0 plus JB. This should be 0 plus JB. So in this way, we can find or define the inductive and capacitive susceptance as given. Now, the admittance triangle for a parallel RLC circuit. What is the admittance triangle? And what is the admittance? So, to understand the admittance triangle, first we have to understand the impedance triangle first. So, for impedance triangle, we know that impedance, the Z, is equals to the vector sum of R and X reactance. So, this is the diagram of a impedance triangle. Now, we know that G is the reciprocal of R, Y is the reciprocal of Z, and B is the reciprocal of X. So here, using the concept of the impedance triangle and putting the value of y equals to 1 by z, r equals to y equals to 1 by z, z equals to 1 by r, and b equals to 1 by x, we can easily draw the admittance triangle. And this is the admittance triangle, where admittance will be equals to the summation of the vector sum of the susceptance and the conductance. Now look, how can you find the value of this V from the last Phasor diagram? You can easily find the value of Y. Yes, Y, the admittance. What is Y? As per the figure, Y is equals to root over V square plus BL minus BC square. So why it is BL minus BC square? Because we consider a RLC circuit, parallel RLC circuit, and we consider the circuit is a inductive circuit. But three element is there. One is resistance, one is inductance, and one is capacitance. But this circuit is inductive circuit, so L is greater than XL is greater than XC. So for that reason, this is G square, the conductance square equals to BL minus BC whole square. This will be the admittance. Here, Y is nothing but 1 by Z. We already defined this. G is nothing but 1 by R, and BL is equals to 1 by omega L, and BC equals to omega C. Where omega, you all know what is omega? Is the angular frequency. Omega goes to 2 pi f. It is the frequency. It's 50 hertz, or somewhere it is 60 hertz. So depending. So you have to follow the problem. Whether it is 50 or 60, you need to use that value to solve the problem. So using this concept, so why it is 1 by omega? Why it is 1 by BC equals to 1 omega C? Because we know that XL equals to omega L, and XL means 1 by BL. So BL equals to omega L. So what will be BL? BL is equals to 1 by omega L. Very simple. And then we know that X equals to 1 by omega C. We have separate lecture for this. X equals to 1 by omega C. For this calculation, the inductance and inductive reactance, capacitive reactance calculation. If you have doubt, please go through that lecture also. That will be very beneficial for all of you. So Xc equals to 1 by omega c. What is Xc? So the relation of susceptance is 1 by Bc, that is equals to 1 by omega c. So Bc will be equals to omega c, where we know that omega equals to, so Bc equals to omega c, omega equals to 2 pi and f. So you have to apply very basic concept to calculate all the parameter, all the element of a parallel RLC circuit. So in this way we can find the current, the resultant current of all the circuit, the current through the resistance, the current through the inductance, the current through the capacitances. Also we can find the impedance of the circuit, we can find the admittance of the circuit, we can find easily the resistance, the conductance, the reactance, and also we can find the susceptance, so inductive susceptance or capacitive susceptance, inductive reactance, capacitive reactance, all the parameters. So using this simple calculation or concept, we can easily find all these values. Now, then we can define both the admittance of the circuit and impedance of the circuit respect to admittance. Yes. So admittance. So in the previous slide, we know that y equals to g square plus bl minus bc whole square, and putting all the value of g. So g is 1 by r whole square, bl equals to 1 by omega l, and bc equals to omega c whole square. Just convert it to the value, and then impedance, we know that z equals to 1 by y, so that is equals to 1 by root over 1 by r whole square plus 1 by omega l minus omega c whole square. So in this way we can find the impedance of the parallel RLC circuit. Now the question is giving us a power factor angle of the circuit, is also giving us a power factor angle. So cos phi equals to g by y. So where phi will be equals to cos inverse g by y, and tan phi equals to b by g. So from the Phasor diagram we can easily find it, or phi equals to tan inverse b by g. So these are the equation from the Phasor diagram we easily find using the simple concept of the trigonometry, the concept from class 9, 10. So tan, if you follow the Phasor diagram, you will find the tan phi equals to b by g. So phi equals to tan inverse b by g, and the cos phi equals to g by y. That means it is equals to cos inverse g by y. The power factor angle also we can find using the same concept. Now, as the admittance y of a parallel RLC circuit is a complex quantity, this admittance obviously a complex quantity, the admittance corresponding to the general form of the impedance, yes, it is coming from the impedance that z equals to r plus jx for AC circuit. For DC it is only r, but for z it is r and x, resistance and reactance. But with the RLC circuit there is a question of XLXC. So you have to consider everything here. So for series circuit we will be written as y equals to g minus jb. For parallel circuit, where the real part is g, is the conductance, and the imaginary part is jb, is the susceptance. In polar form, you know that polar form, that r theta form, a rectangular form, x plus jy form. So in polar form this will be given as y equals to g plus jb. Okay, so that is equals to, if we break it in the magnitude and angle, then the magnitude will be root over g square plus b square, and the angle will be tan inverse d by g. So in this way, we can easily find the admittance of a parallel RLC circuit using this concept, using this equation. So to make this PowerPoint presentation, I take help from different books and also from this link. And my suggestion to all my students, please go through the book, solve different types of books, solve different types of problem from the various books. So the problem solution can make you strong, can clear your concept more and more. And if you can clear your concept once, then you can solve any type of problem, any type of difficult problem you can solve within a few minutes, within a few seconds. You have to realize that for that needs some practice. So please go through the books, read the books. There are so many books, good books are available in the market. So if you have any confusion, you can contact with me, you can communicate with me. So for today, thank you everyone. Thank you very much for watching the lecture.